Okay, let's get started. Logic circuits was a short video on Friday, but we'll continue on from that video here. So there's a brief introduction about digital. Most of the electronic circuits that we use in today's electronic devices are all digital, based on digital. And one of the biggest advantages is, of course, the noise rejection capabilities of a digital signal. Now, obviously, when you convert a analog signal into digital, you have to throw away some information. But depending on the yes, wait. Okay, so PDF, you're asking about the PDF. All right, let me go ahead and do that. I think that's the thing I was trying to remember, and yes, I am. Okay, so logic circuits. Let's go to the right slide. We stopped, or at least the previous video stopped at slide number 8. So binary number system. Why do we actually need to study? Well, us humans, we can work with decimals, we can work with hexadecimal system a little bit, but machines work with binary number systems. This is how Skynet was born. Basically, it takes two states, either on or off. So if you think about a light switch has only two states. It's either on or it's either off, right? So a digital signal, again, it still is voltage and current, but for the rest of this chapter and going forward, we'll think in terms of zeros and ones, right? It's either on or it's off. Now, typically we always talk about positive logic, meaning when the voltage is present, we say it's logic high or logic 1. And when there is absence of voltage, meaning it's close to 0, we say it's logic low or logic 0. All right. So the binary number system allows us to perform these calculations from the perspective of a computing machine. All right. Now, the decimal number system is something we have studied, from elementary school, so we are very familiar with it. So we often don't think how it actually works. But in decimal numbers, the base is 10, right? Is base 10. In binary number system, the base is 2 because there are only 2 values. Decimals, you go from 0, 1, 2, 3 all the way up to 9, so there are 10 values. In binary systems, it's only 2 values, 0 and 1. That's another thing you'll have to get used to. All of the numbers that we deal with always start with a 0. Okay, so I have a table in the next couple of slides which will show you numbers going from 0 to 16. When you have a number, the rightmost digit is known as the least significant bit. So LSB is the least significant bit. Oh, each digit is labeled as a bit. Okay, each digit is labeled as a bit. And the leftmost is the most significant. So in a decimal number system, if we have a number, let's say 1259, then 9 would be the least significant bit and 1 would be the most significant. The same thing in binary number systems. Okay. You can combine 8 bits into 1 byte. So 8 bits comprise 1 digital word. And that's where all of the data storage that we talk about, kilobytes, megabytes, gigabytes, terabytes, that's where the byte comes from. So each byte is made up of 8 bits, and each bit is can take 2 values, either a 1 or a 0. Either a 1 or a 0. So let's see how binary numbers are going to work. Let's take the decimal number at first. 1101.11 in decimal can be broken down as, let's start here. The decimal point is right here. So to the left of the decimal point, it is an increasing exponent. So 10 raised to 0, 10 raised to 1, 10 raised to 2, 10 raised to 3, and so on and so forth. To the right of the decimal is the fraction. So it's 10 raised to minus 1, 10 raised to minus 2, 10 raised to minus 3, and so on and so forth. Right? It's an increasing fraction, means becoming smaller and smaller. So just to the left, we have 10 raised to 0. It's 1 into 10 raised to 0, 0 into 10 raised to 1, 1 into 10 raised to 2, and 1 into 10 raised to 3. So you get 1,000 plus 100 plus 1. And then on the right side of the decimal, you get 1 into 10 raised to minus 1. So 0.1 and then 0.01. If we add all of this up, I mean, if we solve this, we get these numbers. We add up those numbers. That's how we arrive at that decimal representation. Make sense, right? We just don't think about it because, you know, we have been doing this for like more than 15, 20, I mean, 20 years. Our brains are automatically tuned to working like that. Computers work exactly like that with a binary number system. Computers cannot work with decimals because, again, transistors, FETs, they only have two states, either on or off. They have active mode also, but we don't talk about that. We work it in cutoff or in saturation. So remember, in BJT applications, we said it works like a switch. If it's operated in cutoff, it is off. If it's operated in saturation, it's on. That's where it comes from, on and off, right? So computers can perform calculations very, very fast using the binary number system. We just need to understand a little bit of the binary number system, but our brains are not as used to working with binary numbers, okay? So we just do a little bit of introduction in 321. Students can see what the system is, how to perform some simple math with it, and then we move on to like logic circuits. Same number in binary, if I wanted to represent, now everything changes to a base 2. So 1101.11 in binary, base 2, meaning the decimal point is right here. So to the left, we have 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, so on and so forth. To the right, you have 2 raised to minus 1, 2 raised to minus 2, so on and so forth. So you get 1 into 2 raised to 3, which is 8. 8 plus 4 plus 0 plus 1 gives us 13. On the right, we have 1 into 2 raised to minus 1. So 1 divided by 2 raised to 1, 1 divided by 2 raised to 2, 1 divided by 2 raised to 3, and so on and so forth. Now, I can only do up to so much, like half and then like 0.25. Beyond that, I would need a calculator. I'll probably do one more over here, but after that, 1.125, 0.0625. After that, I would need a calculator. But anyway, so you add up those numbers and you get the decimal representation 13.75. 13.75. So this would be the decimal representation of 1101.11 in binary, which is base 2. So base 2 or base 10 is usually a subscript next to the number. So if you see a subscript like this next to a number, that's the base. The decimal would have base 10, binary would have base 2. Does that make sense? Yes.
So if since it's binary is 2, then we have different or it's almost the same. You say something that they have
Same with what?
With factors of 10 you said before. The subscript you said that it can be 2 and 10.
No, we just say base 10 to indicate decimal. It's, yeah.
Is there anything that
What do you mean closer as in? Yeah. It just doesn't work because, I mean, if you think about electronic devices, they can only take 2 states, on or off. There's no in between. If there's in between, then it's analog, it's not digital. So if you think about analog, so let's say the light switch is digital, either on or off. If you have a dimmer switch in there, that's analog, because that theoretically, the dimmer switch can take infinite values. If it's a resistance, you can actually turn the dial and you can stop at any position and you can have a different value of the brightness at any given point. Now, of course, human limitations will not permit that many sensitive motions, but analog is basically infinite, theoretically. So binary is basically just on and off. So only like two possible states. Again, it goes back to how the devices are made, which is like BJTs, FETs, transistors. It's either on or off. If it's in other mode, then it's completely different application. So it's just, well, from everything that we have learned as of now, it doesn't seem possible. But never say never. So here is the table of how a binary number system would look like. All right. First four columns represent binary. Fifth is decimal. Sixth is hexadecimal. We'll talk about this a little bit, I mean, in brief in just a little bit. If you look here, least significant bit. If you just have one digit, meaning just one transistor, it can only take two states. One digit, one transistor can only take two states. It's either 0 or 1, right? Either 0 or 1. So you got 0 or 1. Then that level is filled. You cannot describe any other state using one transistor or one bit, right? So it's one digit, 0 or 1, done. So incidentally, if you want, not incidentally, sorry. Now, if you want to represent more information, you have to add another bit, meaning you have to add another digit. So single digit representation, actually, let's not write single. Number of digits. Number of digits. If only one digit is available, you can have two numbers. If you have two digits available, the most significant bit will first have a 0. Then the least significant bit, you put in 0 and 1, your two states. So you would have a 0, 0 here, and you put down 0 and 1. So now you already have two states. Then once you have consumed both states in the least significant bit, you move on to the next. In a two-digit system, you only have two bits. So once you're done with the least significant bit, you move on to the MSB. Now you switch MSB from 0 to 1. So now you have 1, 1. And then in the least significant bit, you again provide the two states, 0 and 1. Make sense? So now you have a table. So with one bit, you can describe only two states. With two bits, you can describe four states. So that's the number of digits. These are the number of states. If you have three, well, you again follow the same principle. You start with the most significant bit or bits, and then you add in zeros everywhere. So you would add in 0 here, 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 and here. Then you start with the least significant bit, which is on the right side. Fill in the state, so you got 0, 1. Then you move one digit over or one bit over, change that to 1, 1. Again, fill in 0, 1. Now you're done with those two bits. You move on to the most significant bit. You change 1, 1, 1, 1, and then you fill in these four right there. Does that make sense? Do you all see that? This is exactly the same as this, right? So 0, 0, 0, 1, 1, 0, 1, 1. It follows the exact same pattern for the entire number system. And that's it. That's the binary number system. You start off with 0, 1, move on one digit over, you take that 0, 1, you plug it in here. Once you have this 2 by 2 matrix, 8 numbers, then you copy those right here. Now you've utilized all 3 digits. You have 8 states. So with 3 digits, you have 8 states. Yes.
I don't know if you're but like I think another way that I just thought is a make sure this way of perfect understanding it is that the rightmost column could be like 2 to 0, then just 2 to 1, and then
Yes. Yeah, that's, yeah, you're talking about 010101. No, that's how the system would be, because it's only two states, right? So it'll alternate that way. Oh, which power of two? Yeah, well, that's what we saw in the first couple of slides. That's the technical description, right? Because it's going to be 2 into 10 raised to 0. I mean, 1 into 10 raised, sorry, 1 into 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, so on and so forth. That's what it is. But again, because it's only two states, the least significant bit will alternate once every bit. So 0, 1, 0, 1, 0, 1, 0, 1. Second one is the power of 2, 2 raised to 2. So it alternates every two numbers. Third one is 2 raised to 3. So it alternates every three numbers. So 4 zeros and 4 ones and so on and so forth. And if you have 4, then it's 16. Then you plug in zeros, 8 zeros, and then you take this entire table right there, or all these numbers, 8 numbers, and you paste it right there. And there you get 0 through 15, 0 through 15. You always start with a 0. So binary, again, you always start with a 0. So it's 16. The count is 16 numbers, but you always start with a 0. Always start with a 0. So again, machines of course don't have the, this, it's abstract, right? We say it's difficult or easy for machines, but it's exactly the same for all the machines. There's no difficult or easy, it's the same thing, right? But binary number system is what they would work on. For humans, it's very hard to work with, binary number system. Also, if you want to represent large numbers, it becomes very unwieldy, right? Just to represent the number 15, you have to use 4 digits. So to interface with machines and to write programs, they came up with another number system called hexadecimal. Again, so you have 10 digits and 4 and 6 letters, hence hexadecimal, 0 to 9, and then A, B, C, D, E, F. And this is still in use till today. If you look at machine error codes, it will say FF0XX something something. That's where the error codes come from. If you look at the hex codes of the color, it is in hexadecimal. The hex comes from because it is using the hexadecimal system to represent that colored code. Okay. Yeah. So what that error code is telling you or giving the information is the location in the memory where the error occurred. So a programmer or whoever is troubleshooting knows exactly where to go to actually look for that error. Yes. In binary, it would simply be 1010 1010. So let me expand on that. So if we, first of all, it goes from 0 to F, right? How many total digits does it need to describe hexadecimal code? 4. So 4 bits. It needs 4 bits to describe one hexadecimal code, right? So you take 2 bits and you can describe. So in hexadecimal, let me make this smaller. So 1 bit of hexadecimal or 1 bit of hex code requires 4 binary bits. 4 binary bits. So so 8 bits, which is 1 byte, requires 2 hex digits. Okay, so 1 byte requires 2 hex digits. One byte. So I was using the example of color codes, right? Color codes. So if you have 2 digits that you're describing using hexadecimal, your values can go from 00 to FF. In binary number system, it would simply be 0, 0, 0, 0, 0, 0, 0, 0, and 1, 1, 1, 1, 1, 1, 1, 1. Straightforward translation. So how many values do we have? Or sorry, how many bits do we have? 8. So here, think about how many digits. So if you have 1 digit, you have 2 possible states, 2 possible values. 2 digits, 4 possible values, 4 possible states. Base of 2, right? So it's 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4. So if you have 8 digits, 256. 2 raised to 8 gives you 256 possible values. Why is it not coming down? Scroll, come on. And your color wheel, what is the color wheel made of? 3 colors, RGB. And each can take 256 possible values. So the color gamut can run from 0 to 256 possible values for each, comes out to 16,777,000 and 216 values. And that's why whenever they say in a system you have 1,000,000 colors, well, I mean, who can differentiate between 1,000,000 colors? But they're stretching the truth, but it is the truth. Whatever system or light bulb that they have can't actually take these many colors if you actually set it to that color. You can sit there and manually change it, right? You can change it 1 bit at a time by changing the code 1 at a time. So if you change that code 1 at like FF0000 or something, every code will have a value. One of the some software that's a, you know, that have color preferences that you can change. You can set the actual value for RGB by just moving the sliders or just typing in the numbers. So it goes from 0 to 255. So trying to think. I think if you enter RGB all at 255, it turns to white. If it's 000, it turns to black. And then you can move the slider any value in between, you get different colors. LT Spice, which is simulation software, free simulation software, has that kind of setting. You can change it to whatever you want. Anyway, hexadecimal is used to interface between the machine and the human world. One other big application is an assembly language. When I first started out in the 90s, we actually did assembly language programming. And assembly language programming is used when it's known as a low level because so you have the machine and you have the human interface, right? Anywhere in between is basically the entire range of languages. If you talk directly to the machine, you need a very, very low level language. So it's the closer you are to the machine, you are said to be at low level. The farther you are from that interface, you're said to be high level. So like all the, you know, C programming and Python and all those languages, they are high level languages. They need compilers in the middle to actually change our code into a language that the machine can recognize. Assembly language, you use hexadecimal to program the machine directly. You're kind of talking to the machine directly using like a hex keypad. And again, as I said, I started first like in the 90s, 92, 93 or something. So I don't even remember most of that programming. But that's what assembly language programming is used for. So that's another application of hexadecimal. All right, let's see. There is another system called octal where you take 8 values. So it goes from 0 to 7. Well, again, we are not, you know, typically reserve that for like E major classes. Non-E major classes, a bit much. Anyway, that's the binary number system and then the hexadecimal number system. So how do we convert decimal to binary or binary to decimal? You know, the first few values they're quite easy. You got 0, 0, 0, 1, 1, 0, 1, 1, and then you just repeat that for the next few digits. But if you have like a large enough number, you can just automatically write down like 8 or 9 digits. So the way we do it, of course, is, well, I mean, there's a technique. When I say of course, I mean there's a technique to it. So if you want to convert a decimal number, real number, to binary, you divide it by 2. And you want to convert a fraction to binary, you multiply it by 2. Okay. So first, let's look at converting a real number. So the number being converted is 343. So you keep on dividing by 2. You take the quotient and you keep on dividing by 2 while you separate out the remainder. The remainder has to be either 0 or 1, right? It's dividing by 2, so it'll either be 0 or it'll be 1. So if you start with an odd number, and the first remainder is always going to be 1. So 343 divided by 2 gives me 171. Remainder is 1, right? 171 times 2 is 342 plus 1. Make sense? So you take a number, any decimal number, you divide it by 2. Is the base 2. So you keep on dividing the quotient by 2. So 343 divided by 2 gives you 171. 342. So remainder is 1. Again, whenever you have an odd number, the remainder is always going to be 1, obviously, right? So 171 then divided by 2 gives you 85. Remainder again is 1. You take the 85 divided by 2, 42. Now the remainder is 1. But when you take 42 divided by 2, remainder is 0. And so you continue down the line until you're finally left with 2 divided by 2. And eventually you will reach a point where you have 2 divided by 2. 1, remainder is 0. Then as a last step, you would do 1 divided by 2. And that would give you 0. And you will plug in the remainder as 1. So you have to do that as a last step. Otherwise, your answer would be incorrect. So this comes at 171. There, 85 divided by 2, and so on and so forth. The last step is a must. You can take any number. Like, let's take the simple number that you've learned so far, right? We've 5, 7. Let's take 9, for instance. Yeah, question?
No, I mean, so basically, if you get a 1 there, there will be a 0 in the last one. Then if you have instead of a 0 in the quotient at the last one.
We won't. I'll show you.
Oh.
So if it's 9, we start with 9. And you want to convert 9 to binary. You take 9 divided by 2. What do we get? 4. Remainder is 1. 4 divided by 2. Remainder is 2. I'm sorry, quotient is 2. Remainder is 0. 2 divided by 2 gives you 1. Remainder is 0. Excuse me. And as a last step, you do 1 divided by 2. You get 0 and you get 1. Then you read the number in the opposite direction. And you get 1001. If you go back to the table, you can see 9 is 1001. Think on it. Let me know if you have any questions. Something like that, yeah. You can, yeah, it's huge. So the thing is, computers think that way. So if you're a design engineer who's designing the system, that's how the designer has to think. And that's how they have to perform the calculations and design the computer system. Okay. If you are just a user, then we don't have to worry about it. But again, as I said, so it's design engineers who are actually building those systems, they have to think like the machines. As I said, that's how Skynet starts. We're all going to be taken over.
This also applies to the comparison method.
Which numbers? The fractions. Fractions are next to be multiplied. But any questions about this before we move on to fractions? Right? Before enough. When you go to fractions, we simply multiply by 2. And when you multiply by 2, you're either going to get 0 or 1 in front of the decimal, the most significant bit. Right? So you get 0.392. If you want to convert that to a binary number, you multiply it by 2. 0.392 times 2 is going to give you 0.784. So 0.784, you write down the 0, and the 0.784 goes here. Then you take the 0.784 multiplied by 2. Now you get 1.568. Right? So here, let me write it here. So this is equal to 0.784. This is equal to 1.568. This is equal to 1.136. And so on and so forth. And then you take the real part, you write down the real part right here, and you write down the decimal fraction on the other side. And this, you're going to read top down. So you get 0.011001. So 0.011001. For the real number or the real portion, you actually read from bottom to top or bottom up. This is top down. Okay, top down, bottom up. Yes, sorry.
If the product is less than 1, it's a 0.
Where oh, these? So let me explain at the top. So we are trying to convert 0.392 in decimal to binary. So 0.392 is decimal number, and we're trying to convert into binary. So the fraction, which is on 0.392, that's what we're going to try and convert to binary. And so because it's the fraction, we multiply it by 2. So every time we take that fraction and multiply by 2, we'll either get, so 0.392 times 2 gives us 0.784. The real portion is 0, so we keep that 0. And then we take the decimal point, which is 0.784. So this is the correct technical description of writing out the number, but it causes confusion. You see what I'm saying? So we get 0.784. So you write down the 0 from here. Let me actually make this arrow. So this 0 comes here, right? These numbers that are the real portion, they're going to come there. And this 0.784, the remainder, goes in here. And then we take the 0.784 multiplied by 2, we get 1.568. That one real part is carried out, and the 0.568 is separated and written right here. So what this is showing you is that 2 times 0.392 is equal to 0 plus 0.784. This is 1 plus 0.568, right? You're separating out the real portion, keeping only the fraction. And you keep on multiplying by 2 until you get 011. So you get 011,001. Now you read from top down with as many precise digits as you want. If you just want 3 significant digits, then it's just, then 0.392 can be written as 0.011. If you want 5 significant digits, you would go 0.01100. 6 significant digits, you would write the entire thing, 0.011001. If you want to go one more, you do 0.088 times 2, and you keep on going. But you'll get, like, the farther you go, the more zeros you're going to get. Right? Again, thankfully, it's not something that you would encounter that often. Okay, this is just like the basics fundamental that students should be exposed to, but it's, you know, you have to take a step back. Right now, what we're doing is we are looking at the topic like really in depth. We gotta like step back and see what it all, where it all fits in the grand scheme of things. All right, any questions? Yeah. If I have this, definitely, yeah, it'll be specified in there. So binary addition kind of works similar to, you know, what we use for decimal arithmetic, but it's a little bit different. Since it's only 2 digits, if you're adding 0 plus 0, the resulting sum is a 0. There is no carry. Carry is 0. 0 plus 1 gives you 1. Carry is 0. 1 plus 1 gives you 1, 0. Okay. So 1 plus 1 would work like this. You had 1 plus 1, it would become 1, 0. So this would be known as the sum. This would be known as the carry. So we're talking about the least, the most significant bit. And you have 1 plus 1 plus 1. Then the sum, so here, it's 1 plus 1 plus 1. What do we get? Here, let me show you. 1 plus 1 plus 1. You first solve for 1 plus 1. 1 plus 1 gives you 0 and 1. And then you add another 1 to it. You get 1, 1. So this is now your sum. And this is your carry. And that's how you arrive at these rules of addition. You can add, you can keep on adding more and more digits, and you can keep going down the line. Okay, but these are the basic rules of binary addition. 0 plus 0 gives you 0. 0 plus 1 gives you 1. And 1 plus 1 gives you 0 or 1, 0. Two digits. Yes. Circuit designers, they would be doing it. So you would not. Yeah. It's not something that you're gonna be asked to do as a, especially not as a non-EE engineer. Even EE electrical engineers who are working in a different field would rarely ever have to do this. But this is something that's in the syllabus, which your departments tell us that we have to teach their students, meaning you. Okay, so this is not unilaterally decided by the EE department. This is all of your departments coming together and telling us that this is what we want the EE department to teach their students. Okay, yeah. You can, so 1 plus 1 would give you 1, 0. So it'll be 1, 0 plus 1, 0. So 2 digits, then your answer would be 0, and then 1 plus 1 give you 1, 0. So answer would be 1, 0, 0. No, it'd be 1, 1, 0, 0. Okay, subtraction, complements. These are not that kind of complements. These are, well, it's an E. So what does it mean? Complement, the opposite. So we have the ones complement and twos complement. Okay, ones complement is simple. You take the number and you just invert the digits. There's only 2 states. So you take the number, invert the digit. So the complement of 0 is 1. The complement of 1 is 0. Right? So if you have a number, the original number here is basically 0, 1, 0, 0, and 1, 1, 0, 0. That's the original number. That's the original binary number. So the ones complement of this number is simply 1011 0011. Just invert, yeah, invert the digits. That's all. That's the ones complement. But the reason why it's very useful is because when you perform a twos complement, meaning you take the ones complement and you add +1 to the least significant bit. And that resulting answer is the twos complement. Okay. So you take your original number, and you flip it. So you flip the digits, you get the ones complement. And that ones complement, you add +1, which is right here. Add 1 to LSB. Or just add 1, essentially. And the resulting answer is the twos complement. So think about what we just did, right? The addition, binary rules for addition. Here, the least significant bit is 1 + 1. 1 + 1 should give us a sum of 0 and carry forward of 1. Let me do it on the side. So you got 1 0 1 1 0 0 1 1. Anyone's head hurting yet?
For me, yeah.
So take the least significant bit, 1 and 1 gives us 1 0, carry forward 1. 1 + 1 again gives me 1 0. So sum of 0 and carry 1. 1 + 0 now gives me 1 0 1 1 0 1. And that's how you arrive at the twos complement. 1 + 1 gives me 1 0, 0 here, 1 carry forward. 1 + 1 again gives me 1 0, right? 1 is carried over here, and so on and so forth. It's elementary school math. The number system is different, but the it's still elementary school math.
Now you can tell them, what is
That'd be an interesting experiment. But here's the real reason why we do this. Because computers cannot perform subtraction, but they can perform addition. So this is subtraction by addition. So the way computers perform subtraction is by taking the original number and you say, let's say number 1 minus number 2, like A minus B, you would find the twos complement of B and add it to A. And the result would be A minus B. There's beauty in that. So here's the number, and we got the twos complement, right? Now another way of well, actually, let me not confuse you even more. This is another technique of finding the twos complement. Is basically you start from the least significant bit and you keep writing those bits down exactly as they are, right? So 0 0 and then 1. So you're going from this direction, from the least significant bit towards the left. And once you hit that first, or you reach that first one, from that point on, you invert the rest of the digits. And it automatically gives you the twos complement. Yeah, well, that comes later. Yeah. So Sam's holding his head. He's like, that's another way to find it. This is just another way of doing this. So an easier way. Well, I mean, easy depends on your perspective. So, well, anyway, let's move on then. Rain hurts too much, right? Let's do a. So we have about a couple of minutes left. Let's do an example of subtraction. Yeah. So I'll use the same example that they use in the book. So we got 29 base 10 minus 27 base 10. Elementary school math, we should get answer as 2 base 10. Right? So let's see if it works. So 29 without doing any calculation, I'll have to look it up. So it's 0001 and 1101. And then 27 27 is 0, 0, 0, 1, 1, 0, 1, 1. Yeah, that's 27. Okay, so we are supposed to subtract 27 from 29. Oh, here. So 0, 0, 0, 1 right there. Yeah, 0, 0, 0, 1. Okay, so we find the 2's complement for 27. You want to start? We find first the 1's complement. So let's find. Oh, if you need to leave, feel free to leave. It's fine. So 1's complement. You got 0, 0, 1, 0, 0, 1, 1, 1. And then 2's complement would be adding plus 1 to it. And so you would get 1, 1, 1, 0, 0, 1, 0, 1. That's the 2's complement. And now all we do is we add 29 to 2's complement of 27. Okay, 2's complement of 27. 29 was what? 0, 0, 0, 1, 1, 1, 0, 1. That is what we are doing. So this is 29. The resulting answer, 1 plus 1 is 1, 0. Carry forward 1, 1, 1. Actually, I made a hash of it. Let me write this on the side. 1, 1, 1. 1, 1, 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1. So now, starting with the least significant bit, 1 plus 1, sum is 0, carry forward 1. 1 plus 0 plus 0, 1. 1 plus 1, 0, carry forward 1. 1 plus 0 plus 1, again 0 and carry forward 1. 1 plus 0 plus 1 again gives me 0, carry forward 1. 0, carry forward 1. 0, carry forward 1. 0, carry 1. Ignore that last digit. We don't care about that. So we ignore that. Yep, 8 bytes. And what do we get? Only 10 kinds of people in the world. The ones who understand binary, the ones who don't. Now the meme comes full circle. So resulting answer 1, 0, which is 2. Right? Well, this was to show how a computer functions. And so if a designer is trying to create something, that's something they have to keep in mind.
They can do that.
So there are 10 kinds of people in the world, those who understand binary and those who don't. It's a self-explanatory meme. And the next time someone punishes you with 100 push-ups, you know what to do. All right, let's stop right here. We went 3 minutes over time. I think I stopped 3 minutes earlier, so it's a good place to stop.
4 out of 3 people have problems with fractions.
Yes, 4 out of 3 people. Yes, that's a good one. All right, we'll stop here and I will see you all on Friday. Today was